As we kind of wrap up talking about axial load and our axial stress and strain, there's one important topic that we need to touch on when we are dealing with these stresses, right? And this is idea of stress concentrations. And it's not, when you have a bunch of exams all in a row and your stress is all concentrated into one time period, right? It's this idea that sometimes there are stresses that become concentrated because of changes in area. So typically where we see that happening is something having like a drastic change in area, right? This bottlenecking that maybe, if you have a dumbbell shape, for example, let's say you have this is a dumbbell, lifting weights at the gym. You have this change in stress concentration if you were to load this axially. Let's say you were to set the dumbbell on its side and then sit on top of it for some reason. Right? You would have this stress concentration in the handle of the dumbbell here. Right? Where you have this change in area, you have kind of this changing stress. Which makes sense, right? We think about where things tend to fail, it's going to be at these changes in area. Another super common one that we see is anywhere with a hole in it. So maybe you have your bar and it needs to hook into something else, so it has this hole in it that you can, bolt it or nail it, something like that. So it has some hole in it, where now the cross-sectional area has changed, right? It does not include this hole that goes through the middle of it. So because of those changes in cross-sectional area, we get these stress concentrations. And the way we can deal with that is by using stress concentration factors. And a stress concentration factor, I guess I could write it out, stress concentration factor, we usually use this symbol K. And it's just kind of an arbitrary symbol, but we say K is the maximum normal stress in that axially loaded member there over the average stress. And so we can use this in combination with some charts and tables, essentially to design based off of max stress, what can our average stress be? So essentially what we're going to do is we're going to have these series of graphs or tables that allow us to see what the concentration stress factor is so that we can calculate out our average stress. So what I mean by that is the stress concentration factor has these diagrams, right? The one on the left is for a hole. The one on the right is when we have that drastic change in area there. And we can use these to find our stress concentration factors as ratios of those particular attributes, right? So the ratio of the radius to the height, for example, or 2r over w, we can find on this left-hand side graph, and we can use that to find our k value. And it makes a lot more sense when we work through an example of this. But essentially all it's saying is like, okay, if I know I have some allowable stress, some maximum stress that I can use, and I know I have some weird change in area, my hole going through or this abrupt change in cross-section, I know that what I can do is I can use that allowable stress value and find a stress concentration factor so that I can find what the average stress value in that beam is. It essentially allows me to design based off of the maximum stress. This isn't a problem that we encounter a lot. This is really a lot more of a problem for brittle materials, right? Because a ductile material will have a lot more give. But a brittle material is going to fail at these points, right? It's going to break at these abrupt changes in area. So that's really where we care about these stress concentration factors. But let's go ahead and look at an example. So for this example, we're given this odd little bar who has both a hole and a narrowed down neck change in radius. or change in area, I should say. And it tells us that the allowable normal stress for that bar is 120 megapascals, and then we want to determine the maximum axial force we can apply to the bar. So essentially what it's telling us is, hey, okay, if I give you this sigma max, the maximum normal stress is 120 megapascals. What stress concentration factor could you apply so that I have a normal, average normal stress? Find the value of the load for that given the cross-sectional area. So we'll notice that we have both of these changes in areas, right? Both of these stress concentration areas that could cause a problem for us, right? We have both a hole here and this narrowing down. So we're going to have to check both cases to see which one is the limiting case, right? We're going to have to see if the hole or if the narrowing down allows less loading to happen. So what we'll do is we'll go ahead and check our, it doesn't really matter which one you do first, you have to check both of them to see which one is lower. So if we just start with our hole, for example, start with my hole. Let's see what we need, right? We know we're going to need those graphs, those diagrams. So I'm going to go ahead and pull those up for a hole. And it's this one on the left here. And this one on the left here tells me that at the bottom of my chart, in order to get K, I need 2R over W, where 2R is going to be 2 times the radius of my hole, so the diameter of my hole, over the width, the vertical width. So I'm going to pull both of those values off of my diagram here. So so this is the at hole scenario. If the stress concentration limiting factor is at the hole, then 2R over W is a value that I need. And it gives me my 2R value. It's this 20 millimeters right here. So that 20 millimeters over the full height was W. That full W there is 40 millimeters. So that works out to be 1/2. Let's go ahead and look at my chart again. And I know that I have my 2RW is 1/2, which is the very end of my chart here. And it looks like this point lines up exactly on this line. So I can just bring my cursor over here, see what line this is hitting. And it's between 2.0 and 2.2. It looks like it's hitting right smack dab on the 2.1 line. So that tells me that my value for K is 2.1. Now you'll notice they also give me in here this average stress calculation, right? So the average stress calculation, we know it should be the force over area, but here it really takes the guesswork out of what that cross-sectional area is because it tells us it's this W minus 2R. So it's just this little bit of width here times T, the thickness of the thing. So if we were to look at that cross-section, right, here's our cross-section, has the hole in it. So it's just this portion of the cross-section. W minus that 2R value times the thickness T. Okay, what did I say that K was? That K was 2.1. K is 2.1. Sigma max is 120. So we can use our equation. That equation was given to us. K is our max stress over the average stress. So that tells us that our average stress is going to be the max stress divided by K. I'm going to plug that in for our values that we know. We know it is, or our average stress is going to be 120 over that 2.1 K value that we grabbed from that table. And we punch that into the calculator, and that gives us 57.1. 57.1 megapascals. Which then we can go and use that equation, right? You can determine it yourself here, or you can use that equation. And we can say, all right, now my 57.1, that's my stress, is going to be P over A. And again, that cross-sectional area is that W minus 2R times T. That's this area over here. So my W, I can just go ahead and multiply that over to the side. So I get P equals 57.1 megapascals times, so I'm going to go ahead and times 10 to the 6th, so that's in pascals. Then that W minus 2R, W is 40, minus 2R is the 20. So 40 minus 20, and that is in millimeters, so I should probably convert that, to be honest. I'm going to get my units all messy if I don't convert that. 0.02. Converting that to meters, and then my T thickness gave me was 5 millimeters. So this guy times 0.005. That's a 0. There we go. And now I can punch all of that into my calculator and get a P value. So the maximum load that it could handle with applying this stress concentration is, coincidentally, 57.1 kilonewtons. So that's our first option, right? That's the option if the lowest stress concentration, like if the limiting factor stress concentration is at the hole. But we still have to check that other case, right? This was case at hole. We need to also check for case at, I'll do it in blue, case at fillet, I guess I would call it. That's what I would call it if we were using SolidWorks. So we'll just call it at fillet. It's this kind of rounded edge here, this rounded edge that has a radius. This is a circle, an arc, I guess, arc fillet with a radius of 10 millimeters. That's what's going on here. Let's check the at fillet case. All right, so we did at hole, now we'll do at fillet. So now I'm going to need my stress concentration factor chart for the fillet, right? They use two different stress concentration charts. I'm going to go ahead and pull that guy up. He's on the right side here. And I'm going to need two different values, right? I have this R over H on my bottom here, on my x-axis along the bottom. But then you'll see I've got a bunch of different lines. And if you have taken thermodynamics, I'm sorry, no. But if you've taken thermodynamics, you're used to kind of seeing these charts with multiple lines on them. But if you haven't encountered charts like this just yet, essentially what it is we're going to have to determine which one of these lines we have to look at. And in this case, we'll do that by using the W over H value. So there are two values we're going to have to calculate to determine what line to use to get our K value. So first thing, we need R over H, then we also need W over H. Where in this case, our H is the height of the skinny bit, right? Our lesser area. Our W is that full width that it's coming from. And then the radius is the radius of the fillet, of that curving down that it's going. So it's not going like doom, like a hard right corner, like a dumbbell would, but instead it has this nice curved corner, kind of smoothing that transition. So I need W, R, and H. R over H, W over H. Okay, so R over H and W over H. So my R over H is going to be that radius R of the fillet, which is that 10 millimeters. And then my H here, this is the H, is 20 millimeters. So my R over H, 10 over 20 is 0.5. And then my W over H is the full width here. So that's the 40. It's full width here that we found before. That's the 40 over H is 20. So that is 40 over 20 gives me 2. So now I know I'm looking for RH on the bottom is 0.5, and my WH, the line I'm looking for, is the line equal to 2. So if I come back and look at my thing, my RH is the 0.5 right in the center here. The 0.5 line, now I just have to determine which one of these blue lines I'm going to be selecting. And I need the line for W over H equals 2. So here it is. W over H equals 2. It's pointing to this line right here, it looks like. It's a little hard to see. They are pretty close together, but I think it's this. Can I make this guy bigger? Whoop. Not without messing everything up. That's okay. Okay, he's a little bigger now. So he is in between. He's the line between these 3 lines that are all close together. He's the middle line. So I'm looking for that at 0.5, and it's right directly under my mouse cursor right now, which seems to line up exactly with the 1.4 line, right? So I'm at the 0.5 R over H, and then I come up to the W over H equals 2 line, this line, and I come over to pull my K value. That K value is 1.4. That's what it looks like to me. They can be a little hard to read. They're a little messy. Again, if you've taken thermodynamics, you've probably felt this feeling before, but that's just how it is. We squeeze a lot of information onto graphs. What did I say that was? 1.4? Okay, sorry. K is 1.4. K is 1.4. So now we need to go and check. You do the exact same process as we did before, calculating our average stress. So now our average is still going to be that max over K. The only difference is our K value is now 1.4. So 120 over 1.4 gives me a stress of 85.7 megapascals. And then I can do the same calculation that I did over here. I can either find that cross-sectional area here, or I can use the one that they gave me in the table, right? It says my average cross-sectional area N over HT. So it's the cross-sectional area of the smaller area. Right, so that's going to equal my P over HT. So that gives me that P equals 85.7 times 10 to the 6th to get it into pascals. And then H times T, my height was 20 and my thickness is 5 millimeters. So 0.02 times 0.005 to get those in meters. And that gives me that the loading I could have for this one is a very simple math again, 85.7 kilonewtons. So which one of these loads is our limiting factor, right? Which one of these is our maximum load? If you said this guy, that would be correct, right? Our lowest load would be our maximum, which sounds counterintuitive, but if we think about it, if we put this full 85 kilonewton load onto this, what it's telling us is that it's going to fail, right? It's going to fail at the hole because the hole can only handle this maximum. It can only handle a maximum of 57. So if we loaded it all the way up to 85, it fails, right? There's no saving it. And then it's, close to the fillet's failure point, but the hole's already failed. So this is our limiting factor. This is the maximum loading that we could put on this oddly shaped bar. It's the maximum axial force we can apply to the bar. So the key with these stress concentrations is understanding how we use those charts in relation to our average stress and maximum stress so that we can find the correct loadings that we're designing for.